Screen is visible to all.
Yes, sir.
Okay. Because of my pen drive problem, I joined late today. Didn't get the pen drive. Okay. Now today we'll start with module 4. So that is flow through pipes and our dimensional analysis. So that is under module 4. Today we'll start with the module 4. That is part A in that flow through pipes. Okay. So I think already have conducted some experiments in the lab. So same thing will be uh, discussed with respect to theory part here. And the equations or the procedure what is followed in the lab, here in the theory we are going to just use it in other way, so that unknowns in the theory are different, then unknowns in the lab is different. So just to, if you club both the things, so understanding of the theory and lab, once you club them, so your concepts will be clear for us. Okay. So now coming to this part, that is flow through pipes. So here, anytime if you observe, if a complete length of pipe is there without any change in the diameter, so there also we are going to consider some losses. So in the last class I have discussed the Bernoulli's equation, that is, if you can just recall once again, so here what we can recall is, we know the Bernoulli's equation, that is from inlet to outlet for a given pipe or a given flow. One can write it as, for a section 1 for a given pipe here, I can write it as P1 by rho g, V1 square by 2g plus Z1. That is nothing but the pressure head, kinetic head, and the potential head. If you take the sum, that will be equal to the outlet side of the pipe also, inlet and outlet side, or any two sections of the pipe. These two things will be equal. But extra thing what we discussed in that part is also with the head loss. See here, this head loss due to friction here. In earlier chapter we have seen HL. I have taken HL, the head loss, due to which factor we have not discussed. But in this chapter, flow through pipes, we are going to discuss the mainly on this HF. Why I am taking this factor is because in any flow, there will be losses. There will be some leakage losses, there will be some friction losses, okay. There will be some vapor and fluid mixing flow. In such cases, some losses will be there, okay. So there will be different types of losses. So here we are going to focus on that HL or the head loss here due to friction. So that you have to focus in this flow through pipes. Okay. So keeping this in mind, this equation, so we are going to find out what is this head loss HL due to friction. So that is denoted by HF. So coming back to the topic, that is head loss due to friction. So how it is going to take place? So here in any flow, if you consider in the laminar or the turbulent flow, there are two types of flow. So especially in the turbulent flow, if you see, the already I have told you pipe flow. So pipe flow or a channel, closed channel flow, if you see, so these channels are having the entire surface of the liquid is covered by the channel, or the channel or the pipe is having contact with the fluid. The outer surface of the fluid is in contact with the inner surface of the pipe. So that's why we are considering the closed channels. In that, especially in the turbulent flow, what will happen is, in the turbulent flow, we are going to describe the flow in three parts, three types. One is laminar, one is transitional flow, then one is turbulent flow. In the laminar flow, we see that Reynolds number, if it is less than 2300, we classify that flow as a laminar flow. Okay. Or the flow is in between. Say for example, Reynolds number, if you get due to the low velocity or the medium velocity, if the flow or the Reynolds number is between 2300 up to 4000, then we call it as transitional flow, because we cannot differentiate whether it is laminar or turbulent. We cannot differentiate, so we are calling that range as transitional flow. Once it becomes turbulent, the Reynolds number we can note down that is above 4000. If it is above 4000, we cannot say how the type of flow is flowing inside the pipe. So that is called as turbulent flow. So in such cases, when the flow is in turbulent case in the closed channel. In such cases, the head loss will be there due to the friction, or the frictional losses will be more. So what is this friction? It is nothing but the fluid which is experiencing some resistance between the pipe inside surface. Okay, it also depends on the roughness of the pipe also. If the pipe is completely smooth, so the friction losses will be less. And after a long time, or because of the manufacturing problems, if the pipe is rough, if the pipe surface is rough, what will happen? The friction losses will be high. So that fluid is going to have resistance depending upon its roughness. Okay, due to which some energy or the head loss will be there. Okay, so that loss of head due to friction or the resistance of the surface and the fluid flow, that we are going to call it as friction head loss, or the head loss due to friction. Now here, which are those different type of connections where we can observe these head losses? Okay, so I'm not only focusing on friction losses, in different types of losses also. So here, the friction loss we are going to consider it as major loss, because due to this only the head loss or the Bernoulli's equation, what we are going to equate, in that the loss will be high because of this friction itself. So that friction loss we are going to consider it as major loss. So this law of the friction force, how it is going to behave, is described by two scientists. So one is Darcy-Weisbach. Okay, Darcy-Weisbach equation we are going to use in the problems, or in lab also we have used. You can just recall that later. One more is the simplified form of that same Darcy-Weisbach equation, that is Chase's equation. So these two equations we need to remember for this chapter, that is Darcy-Weisbach equation and the Chase's equation for the friction losses. And for the other losses, okay, other losses due to what? Other than the straight flow of the pipe, other than the friction losses, what losses we can see is that is due to pressure drop, or maybe velocity change, or maybe potential head change. So due to that also what will happen? There will be some change in the head. So that how it will be possible is because of the sudden expansion. So where if you see the pipe diameter is suddenly increasing or gradually increasing, so in such cases we are going to consider that as sudden expansion in the pipe. Okay, or in the channel also. It may not be always pipe, circular pipe, it may be different type of pipe also. So these type of losses, other than the friction losses, we are considering it as minor losses. So pipe may be having again sudden reduction in the diameter, like orifice or some pipes which are having sudden reducing in the pipe diameter to increase the velocity for some applications, like nozzle you can recall. So that type of flow we are going to call it as sudden contraction. So in the sudden contraction, sudden expansion, how the losses of the flow are possible, that we are going to discuss. Then in other cases also how this energy and head losses are possible is, one is due to bend. So this bend is an integrated part of the pipe itself, or the pipe itself is bent or it is turned in different angles. It may be 90 degree, 60 degrees, 45 degrees, or any angle. If the pipe itself is bent or it is turned by some angle or in different directions, so that type of connections we are calling it as bend of the pipe. Now elbow is, it is not an integrated part, it is a separate part. So in your home also you might have observed the elbows where the pipe connections are made, the water flow connections are made by using some T shape or the L shape, okay, type of elbows, where the pipes, two different pipes, okay, two different pipes of same material maybe, are connected by using a different component to direct the flow. That type of connection is called as elbow. The elbow is may not be having the same material of the pipe also, okay, and it is not an integrated part of the pipe itself. The pipe is different. This elbow or the turning, the bend of the pipe, what is connected separately, this is separate. So when the separate things are connected to direct the flow, then that change in the angle of the flow or the direction of the flow, what is happening, that connection we are calling it as elbow. Okay. Next is pipe fittings. So now question comes, what are those pipe fittings? So here one thing is, say for example, pressure gauges. In any point, if you want to measure the what is the pressure of the fluid which is flowing in the pipe, or what is the head of the mercury it is showing. So in such cases, we are going to use the pipe fittings. So to connect with the pipe, we are going to connect some devices, or for the same pipe, we are going to channelize the fluid. Say for example, one big diameter pipe is there. From that, I want to collect very little amount of water outside. So that what I'll do, I'll connect one more small diameter pipe by making one some hole. So such type of connections are called as pipe fittings, which is not a same flow of the fluid. It may be a small channel of fluid which is extracted, which is connected from the main connection, or it is a branched connection, you can say. So such type of connections or some devices connection with the pipe, that we can call it as pipe fittings. So in that also some losses will be there. Next is the obstruction. So obstruction is nothing but the sudden reduction in the pipe diameter, that is also called as obstruction. Or maybe like if you see the open channel in which the V notch or the rectangular notch is connected, in that also there will be sudden obstruction will be there. Okay, so in same case we are going to assume it for the pipe also, or you can consider it for pipe also, in which the sudden change in the diameter of the flow directions are given. So there what happens, some obstructions will be there in the flow. So anything if it is reducing the flow rate, or if it is trying to close the diameter of the pipe, or it is going to try to close the flow rate. So such conditions where we are calling it as obstructions in the pipe. Okay, so these are the different various losses which are possible in the flow in the pipe. Only that we are considering in this chapter. Okay, so in this chapter we forget the open channels, notches, or the other meters. So here what we have to consider is, in a pipe given, if the pipe is completely straight, so we are going to consider some major losses, how it is possible by the friction. And in the lab also we have discussed about the major loss or minor loss. We have discussed. So there you might have seen the experiment. So that experiment you can recall here. Okay. So in these two different experiments, one experiment you can see the complete length of the pipe is given, where you have to find out the major loss like friction. And in some other pipe connections, you might have seen the different connections like this: sudden expansion, sudden contraction, bend elbow, pipe fittings, and obstructions. And anyhow, these head losses again we are going to find out again by using the mercury manometer, or the head losses due to the flow rate, that we are again finding by the mercury meter of the pressure gauges also. That's why we are considering again the pipe fittings, how the losses are also possible. So like this, in the different two experiments, also you can recall why in the major loss, the minor losses are not considered. Why? Because there we have considered only the long length of pipe, like 3 meters of pipe we have considered, not with these connections. One more question is, even in minor losses, the pipe length is there. Okay, some straight pipe is there, but still the friction losses is not considered in the minor loss. Why? Because to consider the friction loss, at least some distance should be there. Some long distance of the pipe should be there. Then only the friction losses will be high. If it is very less compared to these losses, like minor losses, if you compare with the friction loss, if the pipe connections are itself are very huge in a given length of pipe, then we are going to neglect these major loss or the friction loss. So that's why in the minor loss experiment, we are not using that friction loss equation to find how much is the friction loss due to the length of the pipe. Because there, what happens, the length of the pipe itself is very small. Only in between, say for example, some 1 feet or below 1 feet, we can find out the pipe is straight. Otherwise, it will be having elbows, bend, sudden contraction, sudden expansion, or some fittings will be there. So due to which what will happen, the length of the pipe will not be same. Okay. So in such cases, we are neglecting the friction losses in minor experiments. In major experiments, we are not connecting the pipe with any different connections other than pipe or other than mercury manometer. So we are in the major loss, we are neglecting these all minor losses. So coming to the other points. So as for the fraud or the fraud loss, we have connected with some points here to understand how the friction loss is related or how these losses are related to the different conditions. So as per Froday's laws, he explains that the friction resistance in the turbulent flow is proportional to velocity raised to n. Okay, so as the velocity in the straight pipe is the connection is continuous.
Yes.
Okay, if any disturbances are there, please unmute your mic in between and tell me. Okay. Yes. So here, Friday has investigated some different things depending upon this turbulent flow, especially, and how these friction losses are dependent on the turbulent flow. So in that, he explained that if the velocity in the pipe flow is very less, so in such conditions, the friction losses are less, and the friction loss is proportional to velocity raised to n. If the velocity is very high, okay, so what will happen? The friction losses will be very high, and this n value may be varying from 1.5 to 2 also. Next is the friction loss is also dependent on the density of the fluid, or you can consider weight of the fluid also. So if the density or the weight of the fluid is very less, what will happen? The contact between the pipe surfaces and the rubbing surfaces will be less. So what will happen? As the density of the fluid is high, the friction losses are also high. Next is it is also proportional to area of the surface in contact. This is very, very important. If the surface area of the pipe is high, means what? If the diameter is high, the surface area of the inner side pipe is very high. So the main observation is how much surface area of the pipe is coming in contact with the pipe. That much amount of friction loss will be there. And after long use, this friction loss also may reduce. Why? Because in the long use, the surface of the pipe may come to smooth, or it will reduce from roughness to the smoothness after long use, or some deposition on the inner surface of the pipe may happen. Okay, so that what will happen? Little bit diameter of the pipe is also reduced. What will happen? The area will also reduce. So after long usage also, without changing the inner diameter, but what will happen depending upon the depositions or depending upon the pipe inner turbulent flows, the pipe surface may also turn from roughness to the smoothness. So there also the frictional losses will be reduced. That is also one of the thing. And continuous cleaning of this inner side of the pipe should not be handled, because of which what will happen? The surface, inner surface of the area will be increasing, and because of the continuous cleaning, the inner surface of the pipe also may become rough, so that friction losses will be high. Okay, so that is one of the consideration. And also he explained that friction loss is independent of the pressure. Okay, so whatever may be the change in the pressures inside the pipe, the friction loss is dependent only on the boundary layer of the surface, which is in contact with the surface of the pipe, or the fluid layer, outside layer, which is in contact with the surface of the pipe. Only that is important, not the pressure. So that he concluded. Also, he told that it is dependent on nature of the surface contact. So as I told you, if the surface is rough, friction losses are high. If the surface is very smooth, for PVC and glass, if you see, the losses will be less. Especially for glass, the friction losses are very negligible. But for PVC, little bit friction losses will be there. For different metals, if you go, what will happen? The roughness of the metal surface may be different. So depending upon that nature of the contact surface, this friction loss is also dependent. So like this, he come out with 5 observations. So that 5 observations are given here. So these observations are told by William Fraud. Okay, so this you can remember, so that anytime if I tell you in the problems, if the velocity is high, what about the friction loss, or if the density is less, what is the friction loss, or depending upon the cross section area of the pipe, how the losses will be affected. So these things we are observing on the major loss. Why? Because it's a friction loss. Is recalling all these points from the friction loss, not from the minor losses. Okay. Next is, he also told that it is independent of the pressure. So it is not dependent on the pressure directly. So it is independent of the pressure. Next is, it is also dependent on the roughness of the surface, of the nature of the contact surface. So I hope until this the points are clear.
Yes, sir.
Okay. Next we'll see how this laminar flow is analyzed, and also the turbulent flow, how these are going to be different. So in the laminar flow, if you see, actually in the laminar flow we are not discussing in this chapter, because only in the turbulent flow only losses are high. In the laminar flow, if you consider, so you can again recall this Bernoulli's equation, where you can neglect this HF or the HL, head losses you can neglect. So laminar flow is what? So already if you recall your experiments, Reynolds number due to the low velocity, and if the diameter is also small, this Reynolds number will be very small. That is rho Vd by mu. If you see, rho and mu will be constant. The changes are what? The velocity and the diameter. If the velocity and the diameter is very less, the Reynolds number will be less. So in this range, below 2300, anytime if you find the Reynolds number, if it is less than 2300, we are calling it as laminar flow. And in this, it will be steady flow, okay, and it is having a regular behavior. One can explain its behavior of the liquid. That is one thing. And the solutions what you get from this laminar flow, any problems if you are solving on the laminar flows, whatever the solutions you get, it may be comparable or it may be almost error free with our experimental results also. So theoretically, if you find out the results and also the experimental values, if you compare both the analysis, if you compare, the errors will be very less. It may be more accurate results you may get in the laminar flow. This is one thing. And in the turbulent, if you see, by Reynolds number, if you recall, it is having the range between 2300 to 4000. It is transitional flow. Above 4000, if the Reynolds number is crossing, then we are going to distinguish it as a turbulent flow. And in this turbulent flow, no one can decide how the flow is going to take place. That is one difficulty. And till now, we are using just the correlations, the possible relations, the possible theories, or the possible different equations, what can decide the flow. Okay, depending upon this Reynolds number or the Nusselt number or the Prandtl number, we have different non-dimensional numbers by which we are going to analyze the this turbulent flow, and using some predictions we are going to solve these problems. So this is very difficult. So in such cases, if you focus on the flow other than the different behaviors, if you focus only on the turbulent flow, it will be irregular, it will be chaotic. One cannot understand also how suddenly the turbulent flow is changing, or how this is unsteady. So one cannot understand. It may be random flow, it may be swirling flow. So swirling means about the axis it is going to rotate, or some eddies or the vortices are also found out. Eddies and vortices means on a given point it is having some small rotations of the particles itself. It may rotate itself by particles, it may rotate about the axis, it may rotate about a given point, or randomly sudden mixing of the fluids may be happening, or it may be creating some chaotic situations. Suddenly it is coming in contact with the surface, some molecules are coming in contact with the fluid particles. So we cannot predict how this flow is going to take place. And Also, we are going to discuss this transitional flow many times. If you want to understand the transitional flow, it should be studied in the 3D. Then only we can understand the solutions. But for the laminar flow, only the 2D analysis is enough, because in entire pipe we are going to assume the flow behavior is steady flow and it is having a regular path. Okay, so here in the turbulent flows, whenever you analyze, so the solutions obtained by the theoretical part will be higher, and from the experimental results, what you get the results will be lower, because losses are actually considered there in the experimental results. So once you consider these two, they will be having some error. So always in the turbulent flow analysis, there will be error. So can you tell me, in your major loss experiment, how you connected this theoretical results and the experimental results? Can anyone recall me what you have used to overcome these errors, or how to find out these experimental results in major loss? Other than equation, other than your theoretical equations or getting the results, what procedure you have followed? So I hope you have used Modi's chart in the lab, or Modi's chart in the lab.
Yes, sir.
Yes. So that indicates the Reynolds number and what other parameter. One side you have Reynolds number, which starts from in between transitional flow to turbulent flow. You have the curves. Then one more axis on the y-axis. Which parameters were there? And what that curves represent? Okay, if you remember, you can recall, or else in the next class you can again go through that Moody's chart and you can recall the parameters what you found out by using that chart, and we'll discuss what is the importance of that chart. Okay, so you take one day time. Sorry, I think Friday we have class. So on that day, sorry, next class is when? Okay, in the next class we'll take this point and we'll discuss what is the importance of that Moody's chart. Okay, Monday. I think Monday is class is there. We'll discuss that, and we'll discuss how that Moody's chart will be helping us to overcome the errors in the turbulent flows. Why? Because here errors will be very high between the theoretical calculations and the actual experimental calculations. So how that chart will help us? Okay. Next is, so I think already you know this Reynolds number equations. I'll not recall once again. So now we'll take the Darcy-Weisbach equation. A small derivation is there on this Darcy-Weisbach equation. Very simple derivation. So here we are going to assume a long pipe as in your experiment. Just all of you, those who have done the friction loss experiment, just recall that experiments. In that experiment, we have 3 different pipes of different materials. So like that, we are going to consider one of the pipe which is having straight connection without any fittings, without any change in the diameter of the pipe, without any obstructions in the pipe. So I'm just assuming or considering one straight open pipe, okay, without any connections, without any changes in the direction of flow, nothing, simple pipe. So here we are considering the flow is from left to right, okay, and we are going to consider section 1 and 2 as per our Bernoulli equation. We need to consider inlet and outlet. And here inside what I have considered between section 1 and 2, the opposing force at the surface, the liquid surface and inner surface of the pipe, whatever the resistance is there, that resistance I am going to call it as F1. So this F1 is the frictional resistance or the frictional force, what is acting in the opposite direction of the flow. That is considered in the sketch. And this small f dash, later we are going to call it as frictional resistance. How much is the frictional resistance? Then we are going to talk about the head loss due to friction. So as I told you, head loss due to friction, we are going to consider it as HF. This HF, extra HF, what is that? Is the head loss due to friction. The earlier class, if I recall it, flow measurement. Yes. Here, if you see the Bernoulli's equation, yes, now the screen is visible. In between, there was connection loss. So where we lost the connection, can you recall? Flow through pipes. This you have started in the earlier part, Darcy-Weisbach equation. You start the class. Now the connection is clear. Just one of you reply.
Yes, sir.
Okay. So I was talking about this equation. The dynamics or other losses what you have considered in this, in the to consider this HL, either you can consider viscous or friction losses, okay, minor losses, major losses, all these losses. We have taken one common term, that is HL. Okay. So similarly here in this case also, what I am doing here is to consider the friction loss, we have recalled this equation with HF. Only that is the difference. Same Bernoulli's equation. So for the simple pipe, we have considered again section 1, section 2, that is inlet and outlet. So these friction losses at the perimeter or the periphery of the circular flow, if you consider the water particles flowing in a pipe, if you consider the outer layer of the fluid, that we call it a boundary layer. That in the boundary, you see that boundary of the fluid as a circular layer that is in contact with the pipe. Here only here the friction losses are there. Okay. In between fluid, if you see the losses, that is viscous force. That is the force is acting is the viscous force, viscosity between the fluid. So there will be that resistance also, like in laminar or in turbulent. But between the different surfaces, if you see, fluid and solid surface, if you see here, in this case, that loss I am considering as friction loss. Okay. So in the analysis, we are talking about F dash, HF, loss due to friction, other things. So for that, again, we have to consider the Bernoulli's equation at section 1 and section 2. So that if I consider at section 1, so where the flow is starting to flow. That section 1 I have considered the pressure head P1 by rho g, kinetic head V1 square by 2g, and potential head Z1. So as the horizontal pipe is connected, later you can cancel this Z1 and Z2. That is one part. At section 2, if you see the equation with the pressure head, velocity head, and the kinetic head and the potential head, right? I can write similarly P2 by rho g plus V2 square by 2g plus Z2. Now, apart from the outlet flow, what is the reduction in the second section? If you see that extra force or the extra head loss, what is considered here is after this length of flow is HF, the loss of head at the section 2. At section 1, we have considered the flow is starting. So we are assuming there is no pipe before this section 1. But at section 2, it is flowing after the length, after say for example length of 1 meter, 2 meters or 3 meters, it is flowing. Then we are going to check the flow rate here. So in that case, the loss of head from section 1 if you compare, so that head loss due to friction in our case, because here we are discussing only the Darcy-Weisbach equation. So now we are considering one extra loss, that is the head loss due to friction. Earlier you have not considered, but in any case if you consider, there will be a losses. So that loss is added, just added with the HF term here. Now keeping in mind that the pipe is not changing any diameter, so inlet and outlet pipe diameters are same. So you can consider the velocity at inlet and outlet is also same. And potential head, if you see Z1 and Z2, since it is horizontal, so I can neglect Z1 and Z2 in the above equation. So if you neglect this V1, V2 and Z1, Z2 in the above equation, I can write P1 by rho g minus P2 by rho g equal to HF. Okay. So similarly, I can again simplify, that is HF equal to P1 minus P2 divided by rho g, because rho g is a common term. So this term is called as HF is due to friction or due to pressure losses will be there in the pipe. Okay, so that pressure losses. So in this case, potential head loss is not there. Velocity losses are not present because of the no change in diameters. So what I'm going to compare, I'm just equating this pressure difference or the pressure head difference with the friction loss. Now, already you know that P equal to rho g h. Similarly here P is what? P1 minus P2. So from this equation I can now write HF into rho g equal to P1 minus P2. So this you can call it as equation number 1. Now important here is to introduce a new term. What is that new term? Okay, that is frictional resistance F1. So what I consider here frictional loss or the frictional resistance, what we have considered F1, that can be written as by the definition, that is the frictional resistance per unit weighted area per unit velocity. So frictional resistance per unit weighted area per unit velocity is given by F dash. Okay, F1 is the total friction resistance. F dash is, small f dash is, what is that F dash? Frictional resistance per unit weighted area per unit weighted area per unit velocity is the small f dash into weighted area into velocity square. Because we are finding frictional resistance, okay, so that frictional resistance per unit weighted area per unit velocity, you can rename it as f small f dash. To cancel that per unit weighted area, I am multiplying with weighted area by dl. To cancel that velocity per unit velocity, I am multiplying again velocity square like this. So we are multiplying the small f dash with perimeter pi d. Pi d is what? The perimeter of the pipe. Circular pipe, if you consider, it is a perimeter pi d. Area is pi by 4 d square. So pi d into L, if you see, I am considering from 1 to 2 length. 1 to 2 is the length, pi d is the perimeter. That becomes the surface area in contact with the fluid, or the wetted surface which is in contact with the fluid. That wetted surface area per unit length I am considering pi d length for a given length into velocity square. So that is v square. So this term I think you have understood F1. So now taking these two terms, considering that forces acting between the section 1 2. So here we found out two different forces. One is the forces due to pressure head, how this P1, P2 is varying. One more term was HF, so that we are just writing it as F1 here. So HF due to F1 as a friction resistance. So now one can rewrite the equations, that is P1 into area or forces if you consider. Okay, before that head loss due to friction. If you try to analyze the forces, because I have considered the friction force, we have here friction force, pressure at the inlet side, pressure at the outlet side. So pressure at the inlet side, if you see here at the pressure side, we know pressure and cross section area of the pipe. Okay, so we know that force is pressure into area, or pressure is force per unit area. From that basis, I can write it as force at section 1 is P1 into A. Force at section 2 is P2 into A. So I am taking minus, or you can take on equal side, or on the right hand side I can write, that is P2 into A plus F1 on the right hand side. Why F1? Because at section 2 there is a friction resistance which is acting between this 1 and 2. So if you take all the terms from left hand side, I can write the force at section 1 minus force at section 2 minus friction loss or friction force, if I consider, equal to 0. So taking the common terms again, P1 minus P2 into A equal to F1. So this F1, what is F1? This we have derived or we have taken from the definition, that is frictional resistance per unit weighted area per unit velocity into perimeter or weighted area, that is pi dl, into velocity square. So that I am taking equal to F dash PL V square in place of F1. In place of frictional force, I am writing it as, or frictional resistance, I am writing it as F dash PL V square. P is what? Perimeter, pi d is the P. Okay, LV square is written here. So now I can write it as pressure difference in the pipe flow, in the given pipe flow is P1 minus P2 equal to F dash P LV square divided by A. So this equation you can consider two. Equation number one is P1 minus P2 into rho G HF. Okay, so now I can tell the pressure difference either due to head difference of the friction head difference in that term, or I can recall the pressure difference in terms of frictional resistance per unit weighted area into perimeter into length into velocity square per unit area, like this. So if you equate 1 and 2, what will get? We will get rho G HF equal to F dash P LV square by A. So just note on these equations, equation number 1 and 2. Then once you equate 1 and 2, I can rewrite the equation like this. That is rho G HF equal to F dash P LV square by A. Now here F dash is the frictional force per unit weighted area per unit velocity. This is F dash. So taking HF, because finally in the Bernoulli's equation we want HF. This, what is this term? Head loss due to friction. What you can substitute in other form. If you directly don't know the HF, then in other terms how we can define it. That is given by this Darcy-Weisel special equation. So now HF I can rewrite as F dash P LV square divided by rho G into A. So here there is a relation between the perimeter and area, because as I told, perimeter is pi d, area of the pipe is, of the cross section area of the pipe is pi by 4 d square. So both we are considering inner surface of the pipe. So d is common here. So taking these two terms, okay, what I can do now? I can write P by A, okay, P by A as 4 by D. If you take the ratio of P by A, because here it is P by A in the equation. So I'm taking ratio of P by A, that is pi by D divided by pi by 4 D square. Means it is nothing but 4 pi D divided by pi D square. So we left it 4 by D. So anytime, even if you don't know the perimeter or area, if you know the diameter also, the ratio of the P by A will be always 4 by D. So from this equation also one can find out either diameter if it is not known, if the perimeter is not known, area is known and diameter is not known, you can find out one of the terms. So now I will replace this 4 by D in the main equation. That is HF equal to F dash 4 LV square divided by rho G into D. You can write capital D or small d, whatever. That is the diameter, inner diameter of the pipe. So that becomes the equation 3. Now next is for the finding of coefficient of friction. What is that coefficient of friction? That is F, not F dash. F dash is frictional resistance per unit weighted area per unit velocity. F1 is the frictional force. Now we have to recall one more term, that is the coefficient of friction, small f. That is given by, small f is given by 2 f dash by rho. 2 times this frictional resistance per unit weighted area per unit velocity divided by rho. That is called as coefficient of friction. So using this relation, I can again rewrite the above equation as what I can rewrite. I can rewrite replacing this f dash by rho. What is f dash by rho? I can rewrite it with the coefficient of friction as f by 2. So why we are taking or recalling all these terms? Because in any problem, if they don't give the coefficient of friction, other term is the frictional resistance. If they don't give the frictional resistance or coefficient of friction, go by frictional force also. So any term we can solve the problems. So with this frictional coefficient, I will replace f dash by rho with f by 2. I am writing it as 4 FL V square square by 2 GB. So from where this 2 and f is coming? It is coming from f dash by rho, which was there in the earlier equation, f dash by rho. That I am replacing with f by 2. Okay. So this is the main equation what you have used in the equation for the lab experiments. 4 FL v square by 2 GB. Or also you can write it as 2 FL v square by GB. That's also can be used. And one more term they have written is 4F. The 4F can also be written as F star. Okay. So F star is again what? The friction factor. So here in this derivation they have recollected many terms. So one is the friction factor, that is 4 times the coefficient of friction, 4F. And one more term is the frictional resistance. Next is the frictional force. So these are the three terms what they have recorded in this derivation. So the derivation either you can write 4F v square by 2 GB or you can write F star into LV square by 2 GB, telling that F star is the friction factor. F star is nothing but force times the coefficient of friction. Okay, so this is all about the Darcy-Weisbach equation. Now, again coming back to the Reynolds number. Okay, so how to find the friction factor? So this is also required from the Moore's chart also, the friction factor. If the or considering this friction factor in the Reynolds number. Okay, so this friction factor is always a function of the Reynolds number also. So if you go by Reynolds number, for Reynolds number less than 2000 or 2300, the friction factor can be written as 64 by R. One can write it there. Or with the coefficient of friction if you want to find out. As I told you, the friction factor is 4 times the coefficient of friction. So if you want to write in terms of coefficient of friction F, if you want to write, so you can divide by that equation by 4. If I divide that, I can write it as 16 by RE. And for Reynolds number from 4000 to above, or up to 10 to 6, if you say, then coefficient of friction F can be written as 0.079 by RE raised to 1 by 4. So these are just correlations. For given pipe, if the turbulent flow is there, so we have found out some correlations directly we are using 0.079 by RE raised to 1 by 4. This is just for understanding. And if boundary layers, so as I told, boundary layer is nothing but the layer of fluids which are in contact with the inner surface of the pipe or the reference of the pipe, the fluid particles which are in contact. So there we cannot tell directly that only the outer layer is in contact, because in turbulent flow, the fluid particles are continuously moving in between. So they will be creating some layer there. It's not a exactly one line of fluid particles. It may be any fluid particle which is coming in that boundary, or which is coming in near to the surface of the pipe. So that layer we are calling as boundary layer. If they are bigger, then the pipe roughness, okay, roughness of the pipe, and the flow is called as hydraulic smooth flow. Means what is the meaning? Whenever this boundary layer is very big, because of the more transitional flow of the turbulent flow, in such cases, where the perimeter of the fluid cannot be considered. Means entire fluid particles are coming in contact with the pipe surface and moving inside. So we cannot decide what is the perimeter of the flow. In such cases, we are calling it as hydraulic perimeter or the hydraulic diameter and hydraulic smooth flow. It's not exactly smooth flow, but we are calling it as hydraulic smooth flow. So that friction factor, or from the friction factor, we can find out the coefficient of friction. So this is given by the Blasius equation. When we cannot define the exact layer which is in contact with the pipe inner surface. In that case, we are going to use this friction factor given by Blasius equation, that is 0.3160 given by RE raised to 0.25. So these are the different friction factors of the coefficient of friction equations used depending upon the Reynolds number. Okay. So next we'll see the simplified equation of the above Darcy-Weisbach equation itself, called as Chase's equation, given in the different parameters. So here we'll discuss this in short and we'll start with the problems. So Chase's equation for loss of head due to friction. So this is nothing but the Darcy-Weisbach equation to find the head loss due to friction HF. So similarly, you recall again the Darcy-Weisbach equation, HF equal to F dash P into L V square by rho G A without implementing any short forms. Because P by A we implemented as 4 by D. Also this F dash by rho we have replaced earlier with other terms. So I have recalled without substituting at this form, or can directly recall this after substitution. But here in the Chase's equation, he has converted the Darcy-Weisbach equation in different form, in his own form. So that is recalled here. So what is the importance of this equation? We'll find out at the last moment. What is the difference between that both equations? Why this is also important? So now in the Chase's equation, what he has done is this area by P, he has taken just reverse. Earlier we had taken P by A. See here, P by A we have taken 4 by B. Now what he has done Chase's reverse. A by P equal to, what is that? P by 4. Why? Because cross section area is pi by 4 d square. And see here, area is pi by 4 d square divided by perimeter is pi d. If you take, the ratio is reverse, d by 4. So this d by 4 he mentioned it as m, factor m. Okay, m is diameter of the pipe divided by 4. Next is, now he put that m term in the equation, so that became f dash by rho g into, earlier it was p by a. So p by a, if I substitute here, it will be 1 by m, because m is a by p into lv square. Now next what he did is, v square he has taken outside, because Chase's want to find out velocity from the Darcy-Weisbach equation, that's all. And after simplification, what he given that equation, that we are calling it as Chase's equation. Now we left with v square equal to, see here, v square equal to hf into rho g into m, hf into rho g into m divided by f dash, okay, f dash into l. I hope the point is clear. What he did, he took v square outside, left side, hf he has taken on the right side. So now we left with hf rho g m divided by f dash into m. Now what Chase's has done is, now he again recalled these terms, rho g by f dash, rho g by f dash into m into hf by m. He segregated again the terms in different ways. So these two terms he recalled once again. He again grouped these terms, rho g by f dash as c, Chase's constant. Okay, so rho g by f dash, we call this as a Chase's constant c, and hf by l. hf is the head loss due to friction, l is the length of pipe. So this hf by l, he renamed it as I. That is loss of head due to friction per unit length, or it is the ratio of head loss due to friction to the length of the pipe. So recalling these short terms m, c and I, he again rewritten the Darcy-Weisbach equation in terms of velocity. So now velocity will be what? Square root of mi, and this Chase's constant itself has taken square root of rho g by f dash. So Chase's constant is taken outside into square root of m into I. I is nothing but hf by l. So m into I is kept in square root. Square root of rho g by f dash itself he has called as Chase's constant. So this equation is almost similar like without K, where we are finding the velocity using some different parameters. So similarly here Chase's equation he wrote the Darcy-Weisbach equation itself in terms of velocity, nothing else. So this velocity is called as mean velocity for the open channels. So in the open channels, if you want to find out velocity, or in the closed channel also, you can use this equation where using this Chase's constant or using these parameters, rho g by f dash under square root and square root of m and square root of h of by m, one can find out the velocity of the channel. Okay. So now we'll take some problems using this Chase's equation and the Darcy-Weisbach equation, similar to your lab experiments, nothing else. Similar to your lab experiments, we'll solve some of the problems and we'll go to the other topic. Yes. So the first problem, in a pipe diameter 350 mm, so 350 mm, we take it as the inner diameter. Length of the pipe is 75 meters. So the length of the pipe 75 meters, it is long. Water is flowing at a velocity of 2.8 meters per second. Find the head loss due to friction using Darcy-Weisbach equation and Chase's formula or Chase's equation, for which the Chase's constant is given here. C is given 55. Assume kinematic viscosity of water as 0.012 Stokes. So again, you go back to the properties of fluid, first chapter, recall the unit, what is the meaning of the Stokes, and later you can substitute in the formulas for the given SI units. Okay, and also I think mu is also given, viscosity of the given fluid 0.012 into 10 to minus 4 meters square per second. So these all values are given in the problem. We need to find out the head loss due to friction by Darcy-Weisbach equation as well as Chase's equation. So first, coming to the Darcy-Weisbach equation, anyone can recall 4FL u square by 2dt. Just directly using this equation, one can find out what is the head loss due to friction. But here in this formula, we don't know the F value of the coefficient of friction, we don't know. Length is given, velocity is given, diameter is given, G is constant. So to find this F, okay, now we have to go by other relations or the standard relations. So that F for the turbulent flow, because we need to find out whether it is turbulent or laminar. For that, we have to find out the Reynolds number. So by Reynolds number, you can find out rho Vb by mu, or you can go by other formula by kinematic viscosity. So go back to the theory. Here, so the Reynolds number can be found out either by using viscosity, dynamic viscosity, rho Vb by mu, or you can use by kinematic viscosity also, that is Vd by mu. So using any one equation, you can tell me what is the Reynolds number for this problem. In this problem, velocity is 2.8 meters per second. Okay. Kinematic viscosity, they have given 0.012 Stokes. Kinematic viscosity is given. So I think by mistake I have taken mu here. It's not mu, it is mu. So as the kinematic viscosity is given, we can find out that kinematic viscosity in SI units. So that becomes around 0.012 into 10 to minus 4 meters square per second. Okay. So if you know the kinematic viscosity, you can write it as Vd by mu. If you know the dynamic viscosity, you can find out by rho Vd by mu. So now by Vd by mu, replace this term as mu and find out the Reynolds number, how much you are taking. Based on this Reynolds number, you have to find coefficient of friction. Yes. Check the Reynolds number. Eight one double six point 667. Okay. So that answer is coming around 8.167 into 10 raised to 5 plus 8.16 into 10 raised to minus 5. Are you getting minus 5 or plus 5? Plus 5 are getting all of you. So if it is for plus 5, so it is crossing 1000 or 4000 value. So by this one can understand the Reynolds number of the flow is in turbulent range. So if it is turbulent range, so for turbulent range, what type of Reynolds number we need to use? For Reynolds number above 4000 up to 10 raised to 6. Okay, so value is, if you take one term outside 8 point something, it is 10 raised to 5. So in this range, I can use 0.079 by RE raised to 1.25 or 1 by 4 for finding the coefficient of friction. In other cases, if they mention any boundary layer of some roughness and other things, then you can go for this Gauss's equation. So keeping that in mind, I'm using 0.079 divided by RE raised to 1 by 4. So friction factor here I'm getting around, sorry, not friction factor, it is coefficient of friction. I'm getting 0.00263 is the coefficient of friction. This coefficient of friction will help us to find the head loss due to friction in the Darcy's Weisbach equation. So I can substitute 4 F as 0.00263, L length of the pipe 75 meters, V square is the velocity 2.8 meter square meter per second velocity square divided by 2G into D. D is diameter of the pipe. Diameter of the pipe is given very less, 350 mm. In mm we have given. So convert that into meters. That will be around 0.35. So head loss due to friction is around 0.9 meters here. So this is the actual process, and we have found out by theoretical relations. But by lab, if you find out, you may get some difference. So that is called as error. So all of you substitute and calculate and check the HF value and the coefficient of friction value. Point 0.002627. 0.002627. Okay. HF value is 0.9. Yes. So all the terms are in meters. So head loss due to friction is also in meters. Because head always we measure in head meters. Okay. So next is first part is over by Darcy's specification. Now next is we need to find out the friction or coefficient of friction of the head loss due to friction by Chase's formula. So recall the Chase's formula, that is V equal to C into square root of M into I. V is the velocity given in the problem 2.8. Chase's constant C, how much we have mentioned, 55, or it is nothing but square root of rho g by F dash. Okay, but here F dash we don't know. F dash is nothing but what? The frictional resistance. That is not given. G is constant. Rho is density of water if it is water. Okay, in the problem they have mentioned water. So that also you can find out F dash, how much will be F dash if the Chase's constant is known. But here directly C's value is given, no need to bother. So 55 or substitute into square root of m into n. So m is not mentioned in the problem. So m is what? P by 4. Or it is reciprocal of P by A. For that I can take it as 0.35 diameter of the pipe divided by 4, that is m, into I. What is I from our derivation? That is HF by L. This HF by L is I, loss of head due to friction per unit length. Okay, so I is not mentioned means you have to write in the detailed part, because in the problem you need to find out HF. L is given. So now I'll write velocity equal to C into square root of m1. C is directly given. M is indirectly given. I is also indirectly given. In that one term is not given. So HF by L equal to 0.0296. So I think HF is not known to us. Okay, HF is not known to us. L is known to us. Yes, L is 75 meters. Is that clear? So don't directly write here 0.0296 equal to I. So just substitute in place of I, HF divided by 75. Then you find out HF. 2.8 equal to 55 under square root 0.35 divided by 4 into HF by 75. So HF is under square root. You can take square root of HF equal to all other terms. Then you can take HF equal to square of answer. To check how much you are getting. Head loss due to friction by Chase's equation. .22. Okay. 2.22. 2.22 meters. Yes. See the error now. How much is the difference? By Darcy-Weisbach's equation, it is around 0.9 meters. By Chase's equation, the losses are very high. 2.22 meter loss is only because of friction loss, which is told by the Chase's equation. And experimentally, if you find out, always the experimental values will be less than the theoretical values. So keeping that in mind, the Darcy-Weisbach equation will give the more accurate or more near value to the experimental results than the Chase's equation. Okay, so these are the values we are just finding by the formula that is given by those people. Okay, I hope this problem is understood to all. We'll take one more problem and solve the plus. Next problem is water is to be supplied. So this is like a application problem. Water is to be supplied to the hostel of the college campus through a supply pipe. Distance of reservoir from the campus. So distance of reservoir, you can assume pump or a underground storage or sump tank, can assume. So from that, the distance of the reservoir from the reservoir from the campus is 3 kilometers. At that distance, our source of water is there. Number of people in the hostel 4,000. Consumption of water per day per person is how much? 180 liters. So by this you can find out for 4,000 people how much water is required. Okay, so like that you can find out some requirements here. Loss of head due to friction. Loss of head due to friction is given in the problem. 18 meters is the loss of head only due to friction from 3 kilometers. 3 kilometer pipe. In the lab, you have seen 3 meter pipe. So assume that pipe has 3 kilometers. Next is, sorry, I think lab we have used 1 meter pipe, correct? In lab, how much is the length of pipe? Now use. Yes, one of you can tell me in the lab what is the length of pipe for this major loss experiment? Okay, I think it is 1 meter. Then in the problem they have mentioned coefficient of friction. Coefficient of friction small f as 0.007 is given. Next is if half of the daily supply is pumped in 8 hours, means for 16 hours full flow will be given, or for 16 hours they will supply the full day. If half of the daily supply, okay, daily supply how much we need to find out? Daily supply to be pumped in 16 hours, half of the daily supply is pumped in 8 hours. Determine size of the main supply pipe. To determine the main supply pipe size means either you can find the diameter, you can find the perimeter, or you can tell me the area also. Okay, so this relates this by d by 4 or 4 by d, what we have taken here, because we need to find out diameter or perimeter or area. So how this problem is related here. Okay, so in the problem assume a reservoir far away from the campus of this hostel. It is from 3 kilometers. The water is pumped there, and in the hostel 4,000 people are there. 180 liters of water is required for one person. So you find out for all the students how much it is. 4,000 into 0.8, so 0.18. Total water required is 720 meter cube. 720 meter cube water is required. Okay. Then for half supply in 8 hours, the maximum flow for which the pipe is required. What they have done here? Total discharge required is 720 meter cube. Okay. From that, for the full supply, for the half supply, 8 hours is required. For full supply, what they have done? 2 times. 2 times into 8. That is nothing but 16 hours. 16 hours if you supply, I will get 720 meter cube of water. I hope you are getting. Just to multiply 2, I have told half supply. Into meter cube per second. To convert that into second. Okay. So here the supply is in hours. To convert that in seconds, we are multiplying to 3,600, or you can multiply with 60 to convert that hours into minutes. Multiply that minutes into 60, you can convert that into seconds. So ultimately, you can multiply with 3,600 into 8 hours into 2 times. Okay. So this will be the total discharge from the pipe. What is required? So meter cube per second you need to find out. One can find out as 0.10125 meter cube per second. This much amount of flow is required per second. Okay. Per day, 720 meter cube of water is required. Per second, 0.0125 meter cube per second of water is required. So why we are finding all these things? Later we need to find out the size of the pipe required. Nothing else. We don't want to find out length of the pipe. Length of the pipe required is 3 km. Up to 3 km we need pipe connection. That is given in the problem. But what we need is how much is the size of the pipe or the diameter of the pipe required. So that can be related later. So first we are finding how much flow rate is required for the hostel. So once you find out all these details, as you already know, Q is connected by continuity equation, that is area into velocity. So for that, what they are doing, for that velocity to find out, I can relate Q by A. But here we don't know A also. Velocity is given. Velocity of the flow is not given in the problem. So what I can do? I can just write V equal to Q by A. That is 0.0125 divided by pi by 4 into d square. So I can write this velocity in terms of diameter. Why? Because in the Darcy-Weisbach equation, we have 4 FL square by 2 GB, where F and L can be known, D is not known. And if it is kept in velocity itself, I cannot find velocity and diameter both in the same equation. So to simplify that, velocity, if you can recall the continuity equation, because of some discharges or the flow rate is given, I can convert this velocity in terms of diameter. Okay, so this 0.0159 divided by d square, you can take it in square. So now coming back to the Darcy-Weisbach equation, HF, head loss due to friction, is given as 18 meters. I'll substitute 18 meters here, equal to 4 into F. F is the coefficient of friction for the given pipe and water. What is that coefficient of friction? It is only for water and the given pipe. For oil and different pipe, again coefficient of friction will be different. The coefficient of friction for water and given pipe is 0.007. 0.007 is taken here into L. What is L? Length of the pipe. Length of the pipe is how much? 3 kilometers. So 3 kilo means 3000 meters. I taken. Velocity we are substituting in terms of diameter. So I can write it as 0.0159 divided by d square into whole square. That is v square divided by 2 GB. 2 into g into d. So now from this, you find out the diameter. So finally, diameter raised to 5 equal to all terms you can take on the other side, and you can find the diameter raised to 5, or directly the diameter value. So please, one of you check this value and tell me the diameter of the pipe or the size of the pipe. How much you are getting? So from d raised to 5, you can take the cube root and square root. You can tell the diameter. So this problem I have taken to understand the relation from the continuity equation or the Bernoulli's equation, Darcy-Weisbach equation, and the interrelation between the diameter and velocity. Means such problems of the application type will relate many chapters also. So one can understand the interrelation between the different chapters. Yes, some answer is diameter is 0.1431 by Varsha, 0.1431 meters. That's 0.143 meters. Or can write in mm, 143 mm. Or if you want to tell in kilometers also, because length is in kilometers, diameter also if you want to tell in kilometers, that also can write. So finally we got the diameter 143 mm or 0.143 meters, or you can write in more detail, that is around 0.1431 meters. Okay, I hope all of you understood the importance of this Darcy-Weisbach equation when you consider the real losses or the actual losses in the pipe. Okay, next class we'll discuss with some fittings how the losses are calculated with some fittings, and we'll recall the equations for the different fittings, sudden expansion, sudden contraction. So for coming to the next class, all of you recall the small equations for the sudden expansion, bend, elbow, and different fittings. Okay, such type of things we'll discuss in the next class. Okay, many are getting the same answer. Okay. Next part is what? Okay, next part is again one more problem is there. After that problem, we'll take the minor losses. Okay. Shall I stop the class here? See, finally you can see the problem just for application what they told. Number of people, this consumption of water, everything they told, just to find finally the diameter. Means discharge can be indirectly related to velocity and area. From area one can find the diameter. Like that they are interrelated. Yes. Add me in the Google Classroom. Google Classroom I have sent I think the class code. Just a minute, I'll send the class code here only. Try here, Chetan Dhanukar. But many are able to join me. Okay, I'll try to invite you. Just a minute. Add. Okay. Just tell me your email ID or send it in the chat box. Like FM lab, I am not taking this time. I am taking only the FM theory for your aeronautical department. You send me the mail ID in the chat box. I'll add in the classroom. Chetan Dhanukar. Is it GIT or GUT? Please type clearly. 1 second you type and send. Sarmeet Chowgule, are you in the classroom? Sarmeet Chowgule. Okay. Any others to be added in the classroom, just inform me. So send me the mail ID so that I will add them in the classroom. Yes, Chetan, now you check. Chetan. Couldn't invite the student. What is the problem here? Just a minute. Invite code. Just turn on only. Invite code is on. Invitation link is there. Students can only come in. And classwork on the screen. Meeting link is also on for all the students. Ready. Okay, try by this link I'll send to you. Chetan, you try by this link.